Alright, so welcome back after the break. So hope all of you had a nice break. I seem to have forgot how to project things. I almost started using my laptop. So hope your midterm went okay. So you should see your grades on Canvas now. Okay, so a TA just entered it this morning, and I have the answer sheets here, and you can collect them after today's lecture. You can also, if you want, come by during office hours today. Alright, so what are we going to do today? So today we'll start, in some sense, the next part of the course, which is, we've done a little bit about basic paradigms, and we've done a little bit about graph algorithms. So now we'll see a few more, somewhat basic, but a little more advanced paradigms. Okay, so and one of them will be randomness in algorithm design. So before going there, a couple of the usual stuff. So we told you midterm grades are out. And also homework 3 is due tomorrow, okay, in case you forgot. So there was a small error in homework 3 that I corrected only yesterday or day before yesterday, something like that. So yeah, sorry about that. It's a small thing, but it's just that it's hopefully you guys didn't waste too much time. Okay, so you just have to make an extra assumption, which I forgot to state. Actually, I thought initially that it would work without, but it takes a little bit more effort to do it without the assumption. Okay, so you can make the assumption. So, alright, so that's about the homework. Any questions, thoughts about the text file? So you for the I uploaded a PDF, but not the text file for the modification. Okay. Yeah, they were almost the same, so I didn't, but I can do it. Yeah. I'm sure you can change the Yeah, any other things? Do people want midterm solutions as well?
Yes.
Okay.
So let's see.
Also, usually I have a midterm review, which will be like a small survey on Piazza. So you can, I mean, it's good if all of you can fill that out. So it's just a few basic questions about the course, some things that, I mean, already half the course is done, so I can't change too much, but we can change a few things. Okay, so that's a small midterm review. So those will be things like, yeah, just feedback about homeworks and stuff like that. Okay. So, all right. So look out for that. Okay, so just a quick recap. So the last couple of weeks before the midterm, we were looking at basic graph algorithms, and there we did shortest paths. We did a couple of algorithms for shortest path, and we also looked at this notion of flows and cuts in graphs. We did this somewhat hastily. Usually, I spend more time on this, but it's fine. I mean, these are. Somehow there's been a general feeling that these are concepts that people don't use as much in algorithm design these days as basics like shortest paths and things like randomized algorithms, which we will see now. Okay, but I just wanted to still recap what these notions were, because we just spent one lecture on them. Okay, so what were flows? So flows are this, so you're given a source and a sink, and you're given a directed graph. each edge had a capacity. Okay. We are thinking of something that is moving from the source to the sink. Okay, so we want some kind of a water flow or something like that, and or a flow of network packets is another kind of example. And each edge has a capacity which is the maximum amount of flow that can go at any particular point of time. And you would like to be able to send as much units of flow as possible from the source to the sink. So this was the max flow problem, and yeah, and we said that this problem can actually be solved efficiently in polynomial time. Okay, so I didn't describe the algorithm, but I mentioned roughly speaking how it works. And we also saw a few things like the greedy procedure gets stuck. And some other, we saw that there is an algorithm called fold-full-person. Solves this problem efficiently. So we didn't see the exact time complexity, but it is something along the lines of m square. Okay, so m is the number of edges, so let me just be conservative and write it as m plus n. Okay, so m is number of edges, n is number of vertices, something like that. Okay, this can be quite bad because m can actually itself be quite bad, can be as big as n squared. So this can be as large as n to the 4. So fold-full-person algorithm is not particularly fast, but it's still polynomial. So that's the general problem of max flow. And again, I just want you guys to be comfortable with the problem statements, because sometimes you see a problem and you think that, oh, this is like a cut problem or this is like a flow problem. Okay? And then you can go and look up algorithms for these problems. So, right, and so the cut problem is in some sense, they also often do the kind of trick that she mentioned, where you just don't, where you make the algorithm interpolate between this kind of a good probabilistic behavior and some brute force solution. Okay. So that's another thing that you can commonly do. Okay. But let's spend one more minute on this Las Vegas algorithm. So what is this? So suppose I change the previous procedure so earlier I just checked pick R random indices and do this. And now I'm saying, so while not found, pick a random index I and check if AF I exists. Okay, so you can potentially do this indefinitely. Okay, but now, so note that this is very similar to just taking a coin and tossing it until you hit heads, right? So in some sense, there is theoretically a possibility that this will go on forever and you will never see a heads. But in practice, you can compute various things about this random variable. Like you can say that the expected number of times you have to toss to see heads is something like 1 by p, which for usual coins is 2, and you also get some nice decay. Right. So this way of looking at things basically gives you this viewpoint that the running time of the algorithm is now a random variable. Okay. So actually, yeah, are all of you comfortable with the use of the term random variables? Okay, so hopefully, otherwise you should brush up a little bit of problem. So the running time of the algorithm in this kind of a viewpoint is now a random variable. And we can now talk about the expected running time, okay, which is what is the, so basically what is the expectation of this random variable. So actually, we'll see much more expected running times in the next class when we'll talk about quicksort and we'll talk about expected running times of quicksort. Okay. So anyway, so this is, so these are what I call last Vegas algebra. So never fail. Can potentially. Okay. Alright, so I want to do, so this was a very toy example, right? So you had a bunch of indices and you promised that n by 3 of them are 0. It looks, it's clearly a concocted example. But what I'd like to show is that there are actually interesting cases where something like this holds. Okay? So this is a very interesting problem. So this is called identity testing. So the problem is the following. Okay? So suppose I give you two polynomials. So one is p of x equals some term, something of that kind, and another where I wrote p of x equals this. And I ask you, is p of x equal to q of x? Okay, so the question is p of x equal to q of x? Okay. So how would you normally solve this problem, right? I'm sorry, I wrote down this thing here, but if assuming you don't read this, right? So how would you test if p of x equals q of x? Identically, if p is identically equal to q.
You plug some extensions.
Well, that's what I wrote here, but ordinarily, right? The instinct would be to expand this out, right? I mean, this was what you would normally do. You would expand out P, expand out Q into some form. If you are ambitious, you can try to factor Q or something, but that's probably hard. Okay. But the easier thing would be just expand P and check that these two expressions are the same. Yeah.
You could also check q of x at the root, so at like 7, 3, 1, x2.
Exactly, yeah. So that's another way you might see. Given that P is in a nice form, you can check if the roots of P are the same as roots of Q, and now you can do something like that. Right? Yeah, but you can imagine P is itself in some semi-factorized form. Like some terms are nicely factorized, some terms are like the Q. In which case, finding the roots is okay. So. Alright, but this is this general problem of checking identities, and as you can imagine, these sort of problems show up if when you have some kind of different parse trees for an expression, you want to evaluate if they are identical and questions like this. Okay, or if you want to test if two circuits are computing the same function. That's another common electrical engineering application where these kind of things are useful. Okay, so. Okay, so this is a very general problem. I have written it only for polynomials of one variable, which is a very special case. Okay. But for this problem, one alternate idea is, I want to check that these two polynomials are equal, right? So I can just plug in some random integer x, okay, and in a certain interval, and now I can evaluate these, right? And note that evaluating this can be pretty fast, okay? Because so imagine these were not 5 terms, but suppose there were some b terms. Okay, so x minus a1 times 2x minus a2, something like this. X minus ab or something like this. Now expanding this out could potentially have like 2 to the d terms. Okay, so if these were degree d polynomials, okay, and right, but even in that case, plugging a value and doing the multiplication is still much faster than actually expanding it and evaluating. Okay, so right, so you plug in a random integer and check if p of x or this. Okay. All right. So now what is the probability of success? Yeah, maybe that's what you're asking.
Yeah, why is tracking the value faster than actual computation? Because anyways you are gonna do the exact same subtraction, addition, and
So that's a good point. So maybe I should convince you guys more of this. Okay, so
in fact, from the perspective of actual computations, tracking would take more time because you do multiple of it.
right. So imagine I have p of x to be something like this. Okay, so if I have x minus a1 times some, let's even have coefficients for the x. So let's have some c1x minus a1, c2x minus a2, c dx. So this is a degree d polynomial, and I have another expression. This is all still a special form, right? Like one is a product and so on. You can have mixtures of these things as well. But so here, let's say I have b1x or b0 plus b1x plus b2x squared. Okay, and these are some parameters. Okay, so now if you had to check by expanding p of x, okay, symbolically, without actually plugging in a given value, then I claim that you have to compute coefficient of each power of x. And if you look at how many terms are involved in these in computing these coefficients, you will actually end up with an exponentially many terms that you could add up. Okay. Exponential in d. Okay. So number of terms in the expansion of p of x is actually, so this is actually exactly 2 to the d. Okay. If you expand naively, you have to make d choices, okay, of which term to. So this is why expanding p of x symbolically is not a very good option. Okay, if d is large. But on the other hand, suppose I ask you what p of 1 is. Now all you have to do is multiply d different numbers. Now you can just do in some order, and this would take roughly d times whatever time it takes for multiplication. So at least if you assume these numbers are all bounded, then this is something like, this is still polynomial in d for sure. Okay. So, and the same with evaluating q. Evaluating q at this one point, p of 1, q of 1 would still, you will evaluate each of these terms and add them up, which is polynomial in d. So, this is same for. So this is what I mean, that evaluating these polynomials at a point is actually faster than expanding them out and checking that these two are identical. And in fact, you can have multivariate polynomials, and this can get much more messy. Okay, so this is so far so good, right? So I've said that evaluating the polynomials is faster, but is this actually a valid procedure? Like if we can, suppose we plug in a random integer in a certain interval, and suppose these two turn out to be equal. Does this mean that the polynomials are always equal? Not necessarily, because you could have, for instance, at 7, maybe q also has a root of 7, and in which case p of 7 equals q of 7, but p and q may not be identically equal. Okay. So the problem is that have p of some value, let's call it a equals q of a, without having p of x identically equal to q. So the symbol 3 equalities means identically equal. Okay, so common notation. So this could happen. But now the question is, can this happen for many A's? In fact, yeah, so in fact, for how many A's could something like this happen? Right, so what he's saying is that there can be at most D different A's for which something like this can happen. And why is that? Yeah, I know you can see, but anybody else? Okay, so why did you say D? Oh, okay.
So basically, the root of the polynomial, if we consider the root of polynomial, both of them can be 0, right? So for example, here, for each term, right, one of can lead to 0. If we have 5 terms here, right?
Yeah.
And for specific x, that term can lead to 0, right?
But you don't need to have both of them being 0. I'm just saying,
Yes,
could it be that p equals q for a certain value of x?
So it's at least D,
Is it at least d?
because there's a D terms over there, D different in P.
Okay.
So like it will have D roots, and in the other one also, if you suppose it has D root, then at least D, and like for P and Q equals 0, that can be the case, and the P and Q are not 0, there can be some of those points as well.
So I think your reasoning is along the right lines, but it's in the wrong direction. Okay. So basically, what he's saying is, there are a bunch of points at which p is equal to 0. It could potentially be that at those points q is also equal to 0, and maybe there are other places where they both are equal to something else, right? So that's fine, but they don't have to be equal to 0 at the same space. But something to note is that suppose you have some a for which p of a equals q of a. Now consider the polynomial, let's call it r of x, which is equal to p of x minus q of x. So these are just polynomials, like p and q are polynomials, so I consider the difference, which is also a polynomial. And if p of a equals q of a, then a is a root of this polynomial. Okay, because if I plug in a, I get r of x equals 0. So any a such that p of a equals q of a is a root of r of x. So this is so you should note that r is also a polynomial. In fact, you know that what is the degree of r? It's at most d, because it's the difference of 2 degree d polynomials. You can't suddenly get a degree d plus 1 or something, so it's at most d. It can be less than d because maybe the d terms just cancel out. Okay. So alright, so I'm saying that any a for which p of a equals q of a is actually a root of this degree less than or equal to d polynomial. Now, how many roots can a degree d polynomial have? D. At most d, right? So, like he's saying, it's not at least d. I mean, sometimes you can have polynomials without any roots, but it cannot have more than d roots. Okay, so So knowing this fact, all I need to do is I pick an interval here which is somewhat larger than the degree, right? So in this case the degrees were 5 and I picked an interval of length 20. Okay. So if I picked a random number there, I know that there are at most 5 different values for which you can potentially have P of A equals Q of A just by luck. For everybody else, you will be able to detect that P is not equal to Q. Okay? And so there's at least a 3/4 probability of success in this process. So now what we have is this procedure, right? So the algorithm can be pick an interval with 4 integers. Actually, it doesn't even have to be 4, right? So let's just write 2 for clarity. Pick an interval with 2D integers, and now the point is pick and let's call this I. And pick a random integer from I. And by what I've argued before, the probability of success is, the probability of this happening without P being equal to Q is at most a half. And then you can see that this is almost exactly the same as the old toy problem that we started out with, right? That most of the times you're guaranteed that. Most of the times you're guaranteed that P is not equal to Q, and you could have this for at most D. Yeah.
I might have missed this, but why can't we justify that our root falls within the range?
Oh, it doesn't have to. It only helps you if it doesn't, right? So look at this. So this is R is the polynomial whose degree is less than equal to D. So it has at most D roots overall over the whole real line. Okay. Now suppose I just pick some 2D numbers. Okay. Now I know that it has D roots overall, right? And if we are, it could happen that none of these are actually roots, in which case you have 2D examples of non-roots. So in which case, if you pick one of these guys at random, let's say none of the roots coincide with these guys, then any of these values will be able to prove to you that P of X is not equal to Q of X. So it works in our favor. Yeah, but that's a good question. Okay. So yeah.
So since R is a polynomial degree less than D,
Yeah.
as long as we have D plus 1 values where R is equal to 0, then can't we stop there without any probability at all?
Yeah. So you're right. So what he's saying is, for this single variable case, you just have to make sure that you just take D plus 1 different points, and just check that P is equal to Q on all of those points. Okay. And if it is true, then they are identically equal. If not, they're not. Okay. So this is a valid test, and totally agree. It's just that when you try to generalize this to multivariate things, then you can have exponentially many roots. Okay. So yeah, so that's another good thing that I was hoping to sweep under the rug, but yeah. Okay.
If we have the opposite case where P and Q are equal, and there's only D roots,
Right, so in this case, if P and Q are actually equal, this R would be identically 0. In which case, R can act, I mean, R is identically 0, so all points are zeros. Okay, so yeah, so that's the R. Okay, so yeah, degree less than or equal to 0. So if R is non-zero, that's this case. So all excellent questions. So anything else? Maybe I should have mentioned, yeah.
You can extend P with fast Fourier transform and you get an MLN.
Yeah. Again, all these are for special case of one variate polynomials. You can do other tricks, but if you have multivariate polynomials, those kind of things also fail. Okay. So what she's saying is that for 1 degree polynomials, there are actually smarter ways of finding the coefficients without actually expanding it out. Okay. And in particular, fast Fourier transform is one way of doing it. But again, this only works for single variate polynomials. But this whole general theory works for arbitrary polynomials of various degrees. Okay, and this is what I wrote here. So there is a general result called the Schwarz-Zipfel lemma, and that tells you that basically something of this kind works for basically multivariate polynomials, even on finite fields and so on. Okay. So, but again, so that's all. My point is to illustrate that sometimes randomness can let you do something cool. Okay, so it's not necessarily to go into the details of this. Okay. So, all right. So that's identity testing. Okay. So the next problem. Okay, so this is, so how many of you have seen this question before? So this is called the problem of primality testing. Yeah.
Sorry, I had a question about the previous stuff. Could you go back to
This one.
I don't understand what R of X signifies.
Right. So R is a polynomial and it's defined as P minus Q. Okay, so P and Q are both polynomials, right, in the variable X. So their difference is a polynomial. Right. So that's what I defined as R of X. Now it could be that R of X is identically 0. If P was equal to Q, all the terms in R would just cancel out. I mean, all the terms of P would cancel out the terms of Q, and R would be identically 0. In which case, of course, it's 0 everywhere. But what I'm saying is that if R is non-zero, then R has degree at most D, because it's the difference of these two polynomials. And that's why it has at most D different roots. Okay, so that's what's. Yeah?
Probability of success in this 1/2.
Oh, if you had a randomized procedure, yeah. So if you picked so if you picked random integer among 2D integers, then there would be at least a half probability. So yeah, if P was indeed not equal to Q, there would be at least a half probability that you will find an integer that P of A is not equal to Q. Okay.
But it's not very low. It's wrong.
All right, so the reason I stopped here is because you can do the exact same trick as we did before, which is you just take multiple samples and you will get this. Yeah. All right. So the next example I'd like to do is primality testing. Okay. So yeah, before that, let's take 1 minute break. I forgot to get my water, so I'm going to drink. So if you have any questions, just I will be back. They send me the yeah.
At the net level, we didn't have any connections, we didn't have very good content.
Okay. Yeah. Hopefully. Yeah.
Right now it's fine.
All right. So next example. Okay. Okay. So the problem is the following. Okay. So this is called primality testing, and this is one very basic problem in number theory and in computer science also. So you're given some integer x, and it has some n digits. So think of n as huge. So it has, let's say, 1,000-digit number. And I ask you, is x prime? Okay. So, and what is prime? Prime just means that x has no divisors. Other than 1 and itself. So how do you normally check if a number is prime? Yeah?
Check the square of the recursive
Square root?
and square of the x. Square root, sorry.
Yeah. So the normal procedure, which I'm sure all of you saw in school, is you are given some number, let's say 10513. So you go up to square root of that number and check if any of those integers divide x. But as you can see, this is if x is an n-digit number, right? So if x has n digits, so then square root of x is something like 10 to the n by 2. This is an n by 2 digit number. Okay. So checking all numbers up to square root of x is clearly exponential in n, which is the number of digits of x. Okay. So again, the key thing here is that you want polynomial in the number of digits. So it's not in the number itself. Okay. So right, so this is a common problem, and this is often also, it has some cryptographic applications as well. So this is a very well studied question. All right, and now the question is, can you have an algorithm that runs in time polynomial in it? So it turns out that there is a very simple probabilistic test that one can do. So unfortunately, I don't think we'll have time to go into this, but this is called the Miller-Rabin test. The way it works is that you pick some integer, some r in the range 1 through x, and you perform a small test on r, which is called the Miller-Rabin test, and you can say that for half the numbers in this interval 1 to x, at least half the number, or maybe 1/4 or something like that, if x were composite, this test would fail. Okay. And if x were prime, this test would always succeed. Okay. So that's the main idea behind this Miller-Rabin test. I'll point out I'll send a link on the course web page. So it's only for interested folks, because
Is it used for unsolved?
partly, and a few other things. It uses nothing very fancy, but it uses a little bit of basic number theory. So, it uses a little bit about the quadratic residues and things like that. But otherwise, simple stuff. Yeah.
And we want to know that if it's divisor of x or not.
No. Actually, that's a good point. So it's not about r being a device, r dividing x or something. So that would still be a test, but you cannot guarantee that this will work for half the numbers, right? Because most numbers will not divide x. Imagine x had only 2 factors, then most numbers will not divide x. Right? Yeah, but this is some test which you can still do in time. That is, it involves some exponentiating r to an appropriate power and so on. But you can still do this in time, that is polynomial in the number of digits. But you will be guaranteed that for half the numbers it will fail. So this was historically this was very significant, because for a long time primality was one of these problems that people could test in if you had access to randomness. Like if you were allowed to do randomized algorithms, there was a test for primality. And somewhat recently people came up with also a deterministic procedure. So now this doesn't sound as cool anymore. But this was one example of a problem where people knew probabilistic algorithms, but they did not know of deterministic algorithms. Okay. Like all the known deterministic things ran in exponential time. So until about 2002, when somebody came up with a nice deterministic. So that's why this problem has a lot of historic significance. All right, so let's, so I just wanted to point out that this kind of things can be done. So, so the next example I will show is a bit more exotic. Okay, so today's class I just want to give a bunch of examples that will show you that randomness can be powerful. Okay, so this is the problem called the perfect matching problem. So it's related to this. One of the questions that we'd seen in class before about like giving gifts to children and so on. Okay, so what is the problem? So you are given a bipartite graph. It's an undirected, unweighted graph, let's say. So it's you have vertices on both sides, and maybe you have some edges. Alright. So let's say you have a bunch of edges, bunch of vertices, and these are called the left vertices, let's call it the right vertices. And your goal is to match vertices on the left to vertices on the right, so that everyone is matched to exactly one vertex. Okay, so that's why it's called a perfect matching. So you want to match vertices to some, and of course you want to match a vertex to someone with whom it has an edge. So a common example of this is an edge indicates compatibility, let's say between two people, and you want to match people, so that match vertices on the left, match vertices on the right, so that you only match compatible. So this is called a perfect matching. And a perfect matching means that everyone on the left is matched. So you can see that in this graph, you cannot have a perfect matching. Okay. Anybody see why? Yeah?
Because there's always going to be one left node on the top part that won't match because of the nodes on the right.
Right. So what he's observing is that there were 3 nodes here whose neighborhood only consisted of these 2 vertices on the right. And there is no way you can match 3 people on the left to only 2 people on the right. Because you want a matching means that everybody needs to be matched to exactly one person. So in this graph there is no perfect matching. But let's say I draw one extra edge. Now there is a perfect matching in this graph, because you can match one to B, 2 to A, 3 to B, and 4 to C. So in this graph now there is a perfect match. Okay. So this is the perfect matching problem. So any question about the problem itself? Yeah, you are just given a bipartite graph, and the question is you want to know if it has a perfect matching or not. Okay, so it's a binary decision problem that I'm posing. Alright, so yeah, has anyone seen how you would solve this problem typically? So the most common way of solving this problem is via a reduction to flows. Okay, so this is one of the canonical applications of flows, but we didn't see that in detail, so we're not going to go into that. So this is one canonical application of a flow. Application of Maxwell. And you'll see that natural greedy procedures don't work and so on. Okay. So, yeah, but a flow algorithm is one way in which you can actually solve this problem in polynomial time. But we'll do it in a different way in this for now. So what I would like to show is that you can actually reduce this problem of finding if a graph has a perfect matching to identity testing. Okay, so this will be a cool reduction. So I'm going to show it. Okay, so think about. So let's say you construct a matrix M where you have n. It's an n by n matrix. Suppose you have n vertices on the left and n vertices on the right. So of course, if the sizes of the left and right did not match, there's no way you can have a perfect match. Right, so you might as well assume that the sides have the same dimensions. So now construct the following matrix M. So it will be what I call a symbolic matrix. Okay, so where suppose there is an edge from I to j. So let's say in this case I look at the edge 1a. So 1a is an edge. So in this case, I write a variable that I will call x1a. So this row corresponds to 1, 2, 3, 4. Columns correspond to A, B, C, D. And if there's no edge, I write a 0. So 1 has edges only to A and D. So here I will write a variable x1b. 2 has an x2a. Oh, here is 0. Four has edges to okay. So is this matrix clear? So I don't have any weights or anything. I just have these variables that correspond to. You can think of these variables as just representing the edge weights if it helps you conceptually. But for now, I just want you to think of them as just some variables. Okay. So I put 0 in this matrix if there is no edge between the two corresponding vertices. Otherwise, I put a special variable that corresponds to that edge. Okay. So is this matrix clear? Okay. And corresponding to any bipartite graph, you can come up with a matrix of this kind. Alright, so now what do I want to say? So the main theorem, the claim, is that if G has no perfect matching, then determinant of M, which I will denote by det M, is identically 0. Okay, so this is what I would like to claim. Okay, so if G has no perfect match, then the determinant of this matrix M that I wrote down is identically 0. Okay, and vice versa. Okay, and if G does have perfect matching, that M is not identical. Okay. So do people understand the claim? I mean, it's a little subtle because this matrix M is not some matrix of numbers, right? It has some variables. These are those these x1a, x2a kind of variables. But I'm saying that the determinant of M, if you think about it this way, is now a polynomial in these variables x1a, x2a, so on. So so do you guys agree with this? Actually, how many of you need a recap of what a determinant is? Maybe. Okay, so that's very good because that's what I was thinking, that maybe that's the okay. So who remembers off the top of their head what determinant is? Okay, what is that?
You like, so you like have to remove like a set of rows and columns to get like until you get to like your base case and solve that.
Yeah, so the most popular definition of determinant is you might remember it from high school, which is you have some big matrix like this. You will draw. You will put your hands like this, and then you will get a submatrix, and you have plus times the determinant of that, and then you'll go to the next row, and then you would have that with the minus sign, and so on. Okay, so this is the determinant definition that you would have seen. But there's also a nicer definition, which maybe I will write down. So if we are given an n by m matrix, let's call it A11. By the way, this example, even if you don't understand it, it's fine. I just want to illustrate the fact that sometimes you can use randomized algorithms in ways which you cannot expect. Okay, but yeah, but it's interesting to follow. So if you have an image like this, one definition of the determinant is you sum over all permutations sigma, okay, of 1 through n. What is a permutation? It's just a reordering. Right? So sum over all the permutations of minus 1 to the power of what is called the sign of the permutation times A1 sigma 1, A2 sigma 2, So has anyone seen this definition? It's, I think some algebra textbooks do it this way. Some algebra textbooks just do it by removing these things. Okay. So if you if you've not seen it, I'm going to introduce what this means. Just to so let me not talk about the sign of sigma. Okay? So sign is just a Boolean 0 or 1 number that you can assign to a permutation. So let's not worry about that too much because that's not needed for our argument. So, but this term is like saying I pick one element here from the second row, one element from the third row, and so on, so that those things are all different. Okay, so that the columns that you pick in each row are all different. Okay, so that's what a permutation gives you, right? A permutation picks. So, for instance, in a 3 by 3 matrix, so if you had A11, so the permutation corresponding to 1, 3, 2 would end up picking first one here, second one here. Okay, so and I'm taking a product of those terms. Okay, and I'm adding up all such products. Okay, with some appropriate signs that are defined that we won't really get it. Okay. So this is one definition of a determinant. Okay. So it's a very inefficient definition. That's why some of you would not have seen it because it doesn't help you actually compute the determinant in a nice way because it has n factorial terms. Each term you have to do some multiplications in order to get it. Right. So that's why you would not have seen it. But this is a but this turns out to be one representation of a determinant. And this is very useful for us, it turns out. Okay, so let's see why. So this is what I would like to claim, right? Like how? So immediately the notion of this permutation should now give you a hint as to why the perfect matching is related to this, right? So basically, if there was a perfect matching in this graph, so let's say something of this kind. Okay, something like 1 goes to D, 2 goes to A, and so on. Now, there would have been one term here, so where you have x1D, x2A, x3B, x4C. Okay, so if I were to pick this term. So the product of these guys would be one of the terms that shows up in this determinant expansion. Okay, because this is a sum over all permutations. Okay, and it's with some signs, and these numbers would have corresponded to exactly these variables. Okay. So the proof of this is that suppose there was a perfect matching. Then the corresponding term the expansion of the determinant is non-zero. And you can check that if there is no perfect matching, right? So let's say you didn't have this edge, then this x1d would have been 0, right? So if you didn't have this edge. So in this case, you can check that if I take any term that shows up in the determinant expansion, like I take one term here, one term here, one term here, something like this, you have to encounter at least one 0. Okay? So that term would become 0. And since we are almost out of time, let me not go into that. But this fact turns out to be true. Okay, that if G has no perfect matching, then the determinant of M is identically equal to 0. And if G does have perfect matching, the determinant of M is not identically C. Okay. So now there is a test, right? So now you have this matrix whose values are some variables, and so the determinant is just some polynomial. And if the graph has a perfect matching, then the polynomial is not identically zero. And now it goes back to the problem that we discussed before, right? Because basically we are saying that one polynomial is just the polynomial 0, other polynomial is this polynomial which is the determinant. Okay. Now the cool thing about the determinant is that there are more efficient ways to evaluate the determinant. You don't have to follow this exponential expansion. There is in fact a polynomial time procedure for computing the determinant, and that is the procedure that you guys know, right? Like this inductive procedure. So but you can do that only if you are given specific values for these numbers. But if you remember, that's exactly what this identity testing is telling us to do, right? So plug in random values and check if the polynomials are equal to 1. Okay. So this turns out to be a very clever way of checking if the determinant is equal to 0 in this case. Okay, so if it's not equal to 0 with very high probability, you will find a counterexample like this. Okay. So yeah, we're out of time, so I won't spend too much time on it. But this is one I wanted to show that there are some. Sometimes it comes with very non-standard applications of these kind of procedures. So let's stop this. Yeah.